Hi guys, today we're going to be doing AQA GCSE Physics Topic 1, Energy, and if you guys would like to check out any more content, our TikTok handle is at _9stars for more study content. Cool, let's get into it. So first things first, what actually is energy? So energy is the ability to do work or cause change. It's what makes things move up, heat up, light up, or even grow. So it comes in a few different forms, so kinetic, thermal, and chemical, just a few to mention, and it's usually measured in joules. And as we can have kinetic, thermal, and chemical, kinetic in moving things, thermal in hot objects, and chemical in like food or fuel. And energy can be stored, transferred, or dissipated. It's never created or destroyed. That's the law of conservation of energy. There are a few more energy stores. So kinetic, thermal, chemical, which we already mentioned. Gravitational potential, which is due to height. Elastic potential, which is found in stretched or compressed objects. Magnetic, so between two magnets. Electrostatic, between charges, so for example between a positive and a negative charge, and two positives or two negatives where those two will repel. And in nuclear, in atomic nuclei, which is covered in greater depth later down the course. So let's take a closer look at energy transfers, basically where energy lives in a system. So energy can be transferred. So we have mechanically by a force doing work, electrically in electric circuit by current, heating due to a temperature difference, or radiation through waves like light or sound. And I've actually left some pictures here, so we may take some chemical energy from an apple and use that to move the bike mechanically. Chemical energy from the batteries allows the torch to light up. And for example, this one here, the plant will absorb the light energy from the sun, and you convert that into chemical energy for growth in photosynthesis. And on the right here, we have a generator motor, where electrical energy causes the motor to spin, which is kinetic energy. However, we also have some of this energy which is transferred to sound energy and thermal energy. Sound energy and thermal energy in this instance is not useful to us, and that is why it's known as wasted energy in this instance. But all the systems follow the same rule. The total energy stays constant, but it changes form. Next up, we're going to go into more conservation of energy. It cannot be created or destroyed, it only changes form or is transferred, and in all systems the total energy remains constant, as we've already mentioned. And I just wanted to highlight this relationship here to you on the right, which we will cover down in a few slides, gravitational and kinetic. So basically these two types of energy, they're interlinked. So as kinetic energy would increase, gravitational potential will increase and vice versa. So yeah. So next up, we're going to look at conduction versus convection, so how heat moves basically. So we know that conduction essentially happens in solids, where particles pass on energy by vibrating. Metals are great conductors because of free electrons, so they're able to conduct the electrical charge in this instance and the heat. And convection occurs in liquids and gases, and it allows for the transfer of heat through fluid movement. So, for example, a hot fluid will rise, cool fluids sink, forming a convection current. So, these are found in kettles, radiators, and Earth's atmosphere. I have put a more detailed explanation here, which I'm going to go through right now. How do radiators produce convection currents? So when a radiator heats a room, it does so by generating convection currents. Heat is transferred from the radiator to nearby air particles through conduction. The air near the radiator gets hotter and becomes less dense because the particles move faster. And this allows for the warm air to rise, and then it's replaced by cool air, which then gets heated by the radiator in return. So meanwhile, the warm air that previously rose gives heat off to the surrounding space. As it loses heat, it becomes cooler, more dense, and then sinks, allowing it to get more heat transferred from the radiator again. So it's a continuous cycle, setting up a flow of air around the room. and that is essentially the basis of a convection current. Cool, so now let's talk kinetic energy numbers essentially. So kinetic energy is the energy of a moving object. It has a formula which comes up a lot every year. Kinetic energy is equal to 1/2 mv squared, where m stands for mass measured in kg, and v is for velocity or speed in meters per second. So essentially, doubling speed quadruples kinetic energy. So if I had my v as 2, and we know that v is squared in this equation, 2 squared would be 4, so it essentially quadruples. And keep in mind here that 1/2 and m are constants because you can't change the mass of an object if we assume it's fixed essentially. And another thing I want you guys to just have a good look at is the joules conversion chart. So essentially, when this comes up every single year, there may be some conversions they've snuck in just to catch some students out. So these conversion charts and units are right here. I recommend you learn them so you're not caught up in the exam, but always please check the units. So then we have gravitational potential energy. So it's basically energy stored by objects lifted above the ground. The formula is GPE is equal to mgh. Never write GPE in your exams because they will not credit it. They will not give you marks for it. So make sure you write out the whole thing. So in this instance, M stands for mass in kg. G stands for gravitational field strength, which is a value of 9.8 newtons per kg. That's the value you should use unless stated otherwise. So for example, in a question they may say use G to be 10 newtons per kg. But if they haven't, make sure you use 9.8. And finally, height, which is in meters. Great. Cool. So essentially, if an object falls, the GPE will decrease and kinetic energy will increase, but the total energy stays constant, essentially, because we're relating that back to the law of conservation of energy, that no energy can be created or destroyed. It always stays constant. And as I mentioned earlier, kinetic energy and GPE are interlinked. So let's take a look at this diagram here. The ball at maximum height essentially has 1,000 joules in GPE, gravitational potential energy. However, as it's starting to fall down, some of that energy is transferred into kinetic energy because it's moving. So then here it's split to 500, 500. And keep in mind that the total here is also 1,000 because the law of conservation of energy suggests that no energy can be created or destroyed. And then when the ball gets to the lowest point, so the lowest point beneath the ground, just above the ground, that's the highest amount of kinetic energy at 1,000. But keep in mind that now that GPE is 0, kinetic energy is 1,000, and the total energy in the system is constant throughout. Cool, so let's not get that modeled up. Now we're going to move on to elastic potential energy in a bit more depth. So it's essentially stored in springs or elastic bands when stretched or compressed, and it has the formula of 1/2 ke squared, where k is the spring constant. This will be given to you in the exam. It will be a number measured in newtons per meter, extension in meters. Keep in mind a conversion trick may be here where they give you the extension in centimeters, so you would have to convert it to meters by dividing it by 100. And this only applies if it's within the elastic limit. So for example, if you had a string, for example, and you continued stretching it out, and then when you let go of it, it doesn't change back to its original shape, that means it's reached its elastic limit. You've deformed it and it won't return back to its original structure and shape. So this equation only applies if the object can return back to its original shape once you remove the forces you've applied. And here are some forces. So when you compress it, it will get smaller, and then when you stretch it, it gets longer. And here on the right is just, again, a visual representation of the equation if you want to look through that again. Cool. And I've seen this come up in AQA quite a few times, the spring extension practical. So essentially what you do is that you set this apparatus up, and this is the weight that you apply. And as you apply more weights, the string will extend more, it will be stretched, and therefore you can measure the extension using the ruler. And when you have the weight and the extension, you're able to actually plot a graph of extension against force. No, wait, of force against extension. Yeah, force against extension, and where the extension will go on the x-axis and the force will be on the y-axis, and a straight line is what you should get, suggesting that the extension is directly proportional to the force applied. And because you'll get a straight line, it shows that it obeys Hooke's law, F equals Ke. Cool. And this is also now we're moving on to specific heat capacity. This is a topic that a lot of students struggle with, but I'm going to simplify it so you guys can understand. So essentially, what is specific heat capacity? It's the amount of energy required to heat 1 kg of a substance by 1 degree. It has the formula E equals mc change in T, where m is mass in kg, C is specific heat capacity, which is measured in joules per kg degree, and the value of that is usually 4.18. And change in temperature means the change in temperature of the actual equipment that's been used, that you would measure using this thermometer here. Keep in mind, if you had a fall in temperature change, your change in T would be negative. So for example, if the apparatus fell by 5 degrees, you would have to write -5. If the temperature rose, in your calculation you would use +5. Cool. So this is a required practical. It comes up a little bit more, but it's also a bit more tricky. So you essentially use the heater on a metal block and measure the temperature change, current, voltage, and time. So essentially you want to create an electrical circuit and measure these values. And then using these values, you're able to calculate the energy supplied. So E, when you do E equals mc change in T. I have listed an 8-step guide on how to actually do this practical. I do suggest that you go over this in your spare time and try learning it, because this is very useful in a 6-marker practical question, and this does come up very regularly. Now we're going to do work done. So work done is when a force moves an object. So it has the formula work equals force times distance moved. So it can be abbreviated to W equals FD. Work is essentially energy transferred and is measured in joules. Make sure not to get caught out with units again. For example, if they gave you kilojoules, you'd have to convert to joules by timesing by 1,000. So I've shown a little picture here of work being done. So this man is pushing this block here, and it's basically applying a force of 20 newtons to get to this position, and it's moved a distance of 10 meters. So if we wanted to work out the work done, the force was 20 newtons and the distance moved was 10 meters. So 20 times 10 is 200 newton meter. No, 200 joules, sorry. Yep, 200 joules. And then we have power. So it's essentially power is the rate of energy transfer. It has a few formulas: power equals energy divided by time, or work done divided by time, and it is measured in watts. Once again, do not get caught up by units. So for example, if it had the kilowatts, once again you times by 1,000. And on the bottom right here, I have put a screenshot of the other related equations, but this drifts more into topic 2, which is electricity. So voltage equals current times resistance, charge equals current times time, power equals current times voltage. But this is more of a topic 2 thing, but I just wanted to highlight that there are some equations that do fall into topic 1 here. Now we're going to be looking at efficiency. So essentially not all energy gets used where we want it to be used. So efficiency tells us how much energy is useful. So the formula is efficiency is equal to useful output over total input, And then if you wanted to convert that into a percentage, you would want to times that by 100. And I've shown you a few ways how they can visualize this to you in exam. So for example, bottom right here, we have 100 joules of electrical energy, and light energy is 10 joules. And the useful, and we would assume that this would be the useful energy. So 10 joules is used in what we want it to be used. So 10 over 100 would give us 1/10. And if we times that by 100, that would give us a 10% efficiency, which is quite low. So when we do have quite low efficiencies, we want to find ways how can we reduce energy loss. So there are three main ways. So lubrication reduces friction, insulation reduces heat loss, and streamlining reduces air resistance. So lubrication, for example, basically is when you apply oil to metals part on your bikes. So on the metal chains, it also helps extend the lifespan, and it helps repel dirt and moisture, reducing the risk of rust and keeping the bike running smoothly and quietly. So as it allows the bike to run quietly, that reduces any energy, that reduces noise. So that's also preventing loss of energy in that instance, as in wasting energy. Sorry, you can't lose energy. And insulating your house, for example, so you may want to use thicker walls from materials with lower thermal conductivity, and there are some methods of thermal insulation. So for example, some homes have cavity walls which consist of an inner and outer wall with an air gap between them. This air gap reduces heat transfer by conduction, as we mentioned earlier. Filling the gap with cavity wall insulation foam further limits energy loss, also reducing convection within the wall space. Loft insulation helps stop convection currents from forming in the loft, which cuts down on heat loss through the roof. We also have double glazed windows, which have two panes of glass with a gap of air between them, which reduces heat transfer by conduction, just like cavity walls. And then finally, we also have drawer exclusors placed around doors and windows to help block airflow and reduce heat loss caused by convection. And the final point leads to streamlining reduces air resistance. So essentially, on this plane, we have quite a pointed tip. This allows the air to come down and move around it, essentially reducing air resistance and allowing us to move quicker and saves energy, essentially. However, for AQA, the main one that usually comes up is insulation, reducing heat loss, so make sure you know this one inside out. Cool, so now we're going to have a quick look at energy sources. So the main non-renewable energy resources are essentially coal, oil, natural gas, and nuclear. They are very reliable, but they are finite. So essentially, we are running out of them. We have a limited supply of them. We can't create them. And the disadvantage is that they have an environmental impact. They produce a lot of carbon dioxide, which may contribute to global warming and thus climate change. And also, extracting these energy sources will actually produce a lot of pollution, whether that be noise pollution by drilling, but also environmental, as they do release other harmful fumes. I have created a table here of the energy resources and their advantages and disadvantages. And for example, biofuels are carbon neutral, essentially that the carbon dioxide absorbed during growth of plants is released when burned. However, it needs a lot of land and may compete with us having to grow crops of food. So essentially, it comes down to the idea, do we grow crops to make biofuels or do we grow crops to make food? And then wind, which is essentially clean and renewable, but I'll go on great depth in that in the next slide. So moving on to renewable energy resources, we have solar, wind, hydro, tidal, geothermal, and biofuel. And we have an infinite supply of them. So they're not running out. They have a low environmental impact, but less reliable. But also, they do have a higher setup cost in a lot of these instances. So for example, the main one they usually ask about is wind energy. And it is clean and renewable. It has no pollution. However, this is very weather dependent. If it's windy, then will the turbines turn, and then generators will generate electricity. And also another thing is that they can be noisy and visually unappealing, which may upset people living nearby them. And yeah, so um, essentially that's that. Hydro requires water, so that's renewable. Solar, you can also talk about the benefits and costs and the disadvantages in setting it up, but once again, it's all dependent on the climate. So there are quite a lot of uses of our energy resources. So in transport, petrol, diesel, which are used in our vehicles, and biofuels. Heating, so gas, electric heaters, solar panels, so heating our homes, for example, and then electricity generation from power stations and wind farms. So now there's also a brief topic in the subtopic in the AQA spec where they talk about trends in UK energy use. It's never really been assessed in great detail, but I think it's important to highlight this. So essentially in the UK, there's a trend away from fossil fuels and towards renewables, and the government essentially has a target to cut emissions. And why do we want to aim for more renewables? Because we want to save our fossil fuels that we have left, and that as supply of these fossil fuels will decrease, the price of them essentially increases. And also, once again, mentioning again the harmful environmental impacts they have, meaning they're not good, whereas renewables have limited environmental pollution. So here's a quick graph showing you the change in energy. So we can see here that nuclear has fallen a lot from 22.95 at its peak in 2016 to only making up 15.29% of our energy makeup. And also a big thing is wind energy. In 2013, only 5.9% of the energy produced was from wind energy generated, whereas in 2022 that shot to 26%, which is massive. However, gas has increased from 26 to 37.91, which is a bit concerning considering that is a fossil fuel and that is not a renewable energy source. In exam questions, there's usually a 6 marker on comparing energy sources. So when it comes down to these questions, you want to essentially consider cost, reliability, environmental impact, and availability. However, please be sure that there is no single best resource. It depends entirely on the need and location. Don't get caught out here. So relating on these lines, we're going to practice a quick question. So what question may look like and the mark scheme to it. So essentially, this question says there are two electricity generation systems. The wind turbine costs 50 grand, the hydroelectric generator costs 20 grand. The average power output from the wind turbine is 10 kilowatts, and the hydroelectric generator will produce a constant power output of 8 kilowatts. So essentially, you want to compare the advantages and disadvantages. And if we look at the mark scheme here, when you want to compare the advantages and disadvantages, you want to talk about both of them as well. So they both have no fuel cost and both have very small / running costs and no carbon dioxide is produced. And then you want to split off onto advantages of wind separately, advantages of hydroelectric separately, and then the disadvantages of wind separately, disadvantages of hydroelectric separately, and then finish it off with disadvantages of both. So they are both noisy, they both may show visual pollution, and then the advantages of wind may be a higher average, which is given to us here. Advantages of hydroelectric is that it's a lower cost. Disadvantages of wind is that it has a higher cost and it has a variable because it says the average power output is not constant like for hydroelectric. And then the disadvantage of hydroelectric is that it has a lower power output of 8 kilowatts compared to the wind turbine's 10 kilowatts. And that's it. So that's pretty much all you need to know for AQA GCSE Physics Topic 1. If you feel like you have any questions, please drop them below and do follow our TikTok. Our handle is at _9stars for more study content. We have produced a TikTok video on topic 1 and yeah, thank you for watching.